Berenjkoub, Rodolfo, Ostilla, Monico, and Bob Laramee.
All right, thank you very much. All right, here we go. I'm glad to be here on behalf of my student Marzieh to present her work on the study of various relations of different flow attributes for the understanding of unsteady flow behavior. So it's a joint effort between the University of Houston and Swansea University. So I was told this is going to be a difficult talk to give because it's not very technical. So Bob, you want to do that? All right, never mind. Okay, let's see. All right, we all know vector fields are important. So they have been widely applied in many critical scientific and engineering applications. So visualizing and understanding vector fields is critical to those applications. So a little bit background. So a vector field is a vector value function, which typically we express it as an ordinary differential equation. And in unsteady case, this function is with respect to both space and time. And its solution given an initial value is a path line, as shown here, which characterizes its geometric aspect of flow. So you can derive number of local flow characteristic or attributes, you can call it, based on the spatial gradient of the vector field, which is also called Jacobian. So with Jacobians, you can derive a number of, I repeat myself, attributes. So those attributes can characterize the amount of change in the flow, or the amount of rotations in the flow, the amount of stress or strain, okay, deformation, stretching in the flow. And you also have other attributes like acceleration, pressure, kinetic energy, and die. Okay, those are the attributes that we are interested in this work. Okay, all right, this is a brief introduction. So with this brief and concise introduction of what vector field and what attributes we can see. So now let's see what people care about in flow. So there are basically two aspects people care about. The transportation behavior of flow, which you can get from the geometric aspect of the flow. You can just visualize integral curves or perform topological analysis. And another aspect that people care about, specifically domain experts, secretly, everybody knows, it's the local physical characteristic of flow, which focus on the microscopic behavior of flow, like infinitesimal rotation, volume dilation, compression, stretching, and scaling. Right? And among them, they're particularly interested in rotation and in general swirling motion of the flow because they lead to vortices, which are the coherent structures that are critical for the understanding of turbulent mechanics. All right, but many times the experts, specifically even in our domain, visualization domain, we focus on just one single attribute, visualize them and analyze them at the time to try to understand the flow. So there's still little work on the study of the joint behavior of those attributes at the same time. So we believe we can do that, we will have additional insight to the flow behavior, especially for unsteady flow. So that's our motivation. So the next question is how to characterize attribute relations. We certainly don't want this, simple scatter plots, right, naive, without spatial information. We want something a little bit more detailed. We want this relation be shown on space so we can correlate them with some flow features. How to do that? The first intuition is let's compute its linear correlation, right? Typically, linear correlation, this is standard, way to compute it. We use Pearson correlation coefficient to compute it. So here is the formula. I believe everybody knows that. It's very simple. The curve measures the covariance of the two variables. Here you can just replace it as two attributes. And then sigma x, sigma y are the standard deviations of these two variables. So in order to get this correlation, you need to have enough samples or realization of these two variables. If you can serialize them and you plot them as two curves, essentially this correlation measures their covariant behavior. If both of them increase or decrease at the same time, you get positive correlation. Otherwise, if one decrease, the other increase, you get negative correlation. All right, so this is the basics. How can we extend it to space, or space and time, right? So people have done it, okay? Soba and the colleagues, introduced the so-called local correlation coefficient, or LCC, to extend this correlation computation into space. So we want to measure the correlation at spatial point, but one point is not enough. It just gives you one pair of value. So in order to adjust that, we consider a local region surrounding that point, and then we put enough samples so we get enough values or realization to compute the correlation. Very neat. Okay, we're going to extend it, as you can guess, right? And later there are a lot of follow-up work to look at different aspects of correlation or correlation classification. But later, people find out simple linear relation is not enough. If you don't believe me, you can go to look at this example. It's called Berenjkoub quartet. I don't know whether I pronounce it correctly, but if you're not familiar with that, just Google and see. This is a nice illustration why linear relation is not sufficient. Then people start looking at mutual information, like the previous work. Okay. All right, so the mutual information computation is based on information theory. You compute a bunch of entropies of the variables and variable relations, and then from there you get the mutual dependency of those variables. So scientists have actually applied this in various locations, for instance, to reduce the uncertainty in visualization or try to identify salient structures from scalar field. All right, so our work extends this correlation and mutual information computation to unsteady flow, and then we applied it to both Eulerian and Lagrangian views. So we have boldly said we are not the first. All right, so clarification, what I mean Eulerian view and Lagrangian views. So people doing flow with already know that. So Eulerian view means that we observe flow in fixed location. Okay, samples are not moving. Okay. And in contrast, Lagrangian view, we observe the flow at moving particles, so basically look at the relative behaviors in the flow. All right, so with that clarification, I just have a quick overview of our contributions. We defined a number of metrics to quantify both linear correlation and nonlinear dependency among different flow attributes in both Eulerian and Lagrangian views. We devised a number of visualization techniques to show the results. And then we applied to a number of use cases to measure their effectiveness of the metrics, okay, in terms of reviewing different relations among attributes. So our metrics, very simple. Okay, the first metric is just a simple extension of the LCC you have seen. Instead of getting the realization on a spatial region, we extend it to space and time. Right, this is a nice illustration. So in Lagrangian views, we just have a spatio-temporal kernel wrapping around a portion of the path lines. And then we take the samples within this local region, and then we get the realization of those values for our correlation computation. Very simple, right? And then we extend it a little bit. Instead of measuring the correlation of scalar values, let's measure the correlation of vector values. Okay? So the formalization of the correlation computation is still the same. The only difference is how we compare two vectors. There we introduce a metric to compare the difference of two vectors by comparing their difference in direction and magnitude respectively, and then combine them. Right? And the rest is the same. Okay. And for mutual information computation, there's really not much we can say. We just apply the standard definition. Okay, but we just get the entropy computation from the values we get from the spatial-temporal domain. Okay, and then there are multiple formulas that you can compute the mutual information which measure the dependency of attributes. Sorry, go back. All right, so it's very intuitive to understand. So if you take the attribute x as the beginning, and then if you have enough variation, the entropy of this variable will be large. And given the knowledge of y, and then you look at the uncertainty of the attribute x, if the uncertainty is low, it means that if I know more about y, I also know more about x. That means what? It means they are highly dependent with each other. So if we minor this, you get a larger value. So which means that they're highly dependent of each other, okay? All right, so with these three metrics, okay, we just compute, we call it correlation and dependency fields. So we uniformly sample the domains many seeds, and then we compute the correlation or mutual information values using the previous introduced metric in either Eulerian view or along path lines. Okay, and then we store the values at the sample location. This gives rise to scalar fields. So it's easy to visualize it if it's a scalar field. So for 2D, we use color plot. For 3D, we use direct volume rendering. And the color coding we use naturally is divergent color scheme because of the nature of correlation, positive or negative, right? We use the traditional blue, white, red color scheme and its variation. We use red to represent positive correlation and blue to represent negative correlation. And we use the same color scheme for mutual information. So blue means low value and red means high value. Okay. And I forgot to mention mutual information is always positive. All right, and another visualization we introduce is we encode this correlation along path lines so that we can actually see the temporal behavior of those correlations along the advection of particles over time. Finally, we introduce a ranking-based segmentation. So instead of compute just one pair of correlation, okay, at each sample we compute multiple pairs of correlation from a set of attributes of interest. That means instead of just one value in a sample, we have multiple values corresponding to the correlations of different pairs of attributes. Then we rank those values, and then based on the top rank pair, and we color code the domain, which gives us something similar to a segmentation, as showing this example, which allows us to see in what regions which pairs of attributes are more related to each other. For instance, in this example, this is a flow behind cylinder in 3D, and we can see in the vortex shredding region, okay, the core, the acceleration and Q attributes are highly correlated. It's the dominant correlation there. And at the boundary layer of this vortex shedding, the acceleration and shearing is the most dominating pair. And outside of it, shearing and Q value are both small. That's why they're correlated. All right, more results. So to assess the effectiveness and understand what they can measure, okay, of those different metrics, we applied it to a 2D flow behind cylinder data sets. We know this forms a vortex shedding, okay, behind the cylinder. So we use the norm of the Jacobian and the local shear rate as the pair of attributes for the study, and we look at the Lagrangian view. Okay. So from this result, we see in STLCC the correlation. We see a strong negative correlation in the vortex region. This is understandable because they have negative behavior over time, especially for local shearing. It's decreasing towards the vortex, okay, right? Because dominant characteristic there is rotation. Shearing measures the stretching, while the norm is high there, okay. And similarly, if you look at the ST vector, okay, the vector-based STLCC, we find a strong negative correlation at the boundary layer of vortices. This is also easily understandable because if you move towards the vortex, okay, the norm of the Jacobian is increasing, but again, the local shearing is decreasing. That means the gradient direction is pointing away from each other. Therefore, they have negative correlation there. Okay, so in contrast to the STLCC and the ST vector LCC, the mutual information actually highlights, the boundary between, two groups of counter-rotating, oppositely rotating vortices. Well, at those places, things changing a lot. Okay, there's a lot of variation, which means that the entropy there is high for both attributes. Okay, based on definition, they're highly dependent. All right, now let's look at the difference between different views. Eulerian versus Lagrangian. We use the same data, and then we use the same pair, norm of Jacobian and local shearing. All right, we already note the local shearing actually highlight the vortex structure, and in contrast, the Eulerian view of the STLCC tend to review the overall behavior of this flow. Okay, as you can see, the two blue bands in the lower image actually correspond to the places those vortices go through. So we average the flow. Okay, so that's the difference of the correlation in these two views. All right, now let's see how visualizing this information on path lines can help with revealing more information about vortices. Okay, we use the homogeneous charge compressor ignition. Try to remember this name. HCCI dataset as an example. We sample a number of path lines in different locations of the flow. Some of them are sampled close to the core, as you can tell. The flat path lines are sampled near the core, and others are sampled far away from the core, the helical path lines. So we see something interesting, right? The correlation along the path lines, sitting at the curve, at the core of the vortex, tend to be quite stable if it's not constant, while the correlation along the path line sitting not at the core are quite fluctuating. Okay, to better understand it, we just look at the plot of the realization of those two attributes in the spatial-temporal kernels. So let's focus on the samples along path lines seated at the core. Okay, as you can see, the behavior of the two attributes at the two sample positions are quite similar. So that explains the consistent or stable of the correlation over time. So in contrast, if you sampled the two time position along the path line seated off the core, you see their behavior are changing over time. Okay, the trends are changing. So that explains the fluctuation of the correlation you see along the path lines. Okay, you can see this even better in the mutual information visualization. So I have to move on. So here's another data set for large ocean. So you can see STLCC highlight a band of strong eddies in the equator, while the mutual information tend to highlight strong offshore currents near the east coast of individual continents. All right, one final data set, I promise. We have more results in the paper, but sample one more data set because this is new to the flow visualization committee, so I want to bring this up. So these data sets simulate two parallel counter-rotating vortex tubes. Okay, so there were two scenarios. The top scenario undergoes, we call it elliptical instability. It means that during the direction of these two vortex cubes, they tend to interact with each other, and the structure break down quickly and lead to chaotic. And the second scenario, it's not that chaotic. It leads to, we call it vortex reconnection. So we simulate the two attributes, vortices and the die. Okay, the die is, people really know the die in physics, we drop the die. But in numerical, it's a passive scalar with a Schmidt number of unity. So the formulas of the direction of these two attributes are shown here. You see there's a term difference between these two formulas. If you take out this term, and the two formulas are exactly the same. So the experts expect there will be some difference in the correlation in these two scenarios, because the instability case, we have a stronger vortex stretching, but for the reconnection, the first term is ignored. So the correlation must be different. But if you look at our results, it tells otherwise. They are all strongly correlated. Okay, this forced the experts to go back to think their theory, why it's not the case they want. And eventually they find out it's because of the Rhino number he used for the simulation is not high enough, okay, to make this first term matter for the first scenario. So this is how our simulation, or how our technique helped the experts to improve their simulation. All right, I don't have enough time, so performance reports. So we implemented in GPU, so it's not really fair to compare to CPU. Okay, this is highly parallelizable. And then parameter study, okay, I leave it for the Q&A because we have two important parameters. One is the size of the spatial kernel, the other is the size of temporal kernel. So they have some effects to the patterns we get from the correlation study. So with that, I conclude my talk. And there are a lot more results and conclusions that you can find. I think the strength of the paper is not really the technical part, it's the results using these simple techniques. So I encourage you to actually read the paper and learn more about what you can see from this correlation study. So future work, we want to extend to more directions. And then I want to thank you, a bunch of people, especially lay, who makes significant contributions for laying out the foundation of this work. And funding agency, we said thank you, and I'm happy to answer your questions.
time for one quick question. Please come to the microphone. State your name and affiliation. No question. So I've one question. When I saw the individual path lines, that's maybe one question also for Bob, because I know that you did some clustering work of integral curves. Did you think of coupling what you did with the clustering?
That's a very good suggestion for future work, actually. No, we didn't think of that, I think.
Okay, so just to repeat, you didn't think of it yet, but you think it could be a good contribution
in
maybe.
Future work. Yeah, definitely.
Okay. All right.
Always. Okay, thank you.
Thank you very much.